Right. Hello everyone. Today we're going to be talking about special relativity. So there's a few different experiments where special relativity is involved. Um, the first one that you have to know is about muon decay. So we'll go through what muon decay actually is and how that kind of proves special relativity. So these little black dots over here, they represent muons, okay? And those muons, they're very small particles and they are created in the atmosphere. Now they're about 10 to 15 kilometers above the surface of the Earth. So this distance here is about 10 to 15 kilometers. So, they're way up in the atmosphere. But they have a very small half-life, okay? So their half-life is only 2.2 microseconds, but they move very fast. They move at 98% the speed of light. So because they're moving so close to the speed of light, they'll experience this thing called special relativity. And they'll actually experience time dilation. I will talk about how the scientists they actually know that they do experience that time dilation. So these muons have a half-life of 2.2 microseconds. If we think about it in classical physics, so that's like Newtonian physics and linear motion, then we would predict that the muons would decay at probably around this point. So we would predict that they would reach here before they would be decayed, and you wouldn't find any of these muons on the surface of the Earth. That is what scientists expected if they approached it with a classical physics viewpoint. But because of special relativity, these muons, these little black dots, they actually undergo a thing called time dilation. So because these little black dots, they're moving so fast at 98% the speed of light, they actually experience time slower. So at their viewpoint, or their frame of reference, their 2.2 microseconds is still their half-life. But for them, they're moving so fast that they experience time slower. If we pretend that we're an experimenter on the ground, a bit of a giant, but these experimenters, they went and they counted the number of muons that they found on the surface of the Earth. And what they found was there was a lot more muons on the surface of the Earth than they expected. They weren't expecting to find any because they thought they would have all been decayed because of their short half-life. However, they set up instruments and they actually recorded a large number of muons that actually reached the surface of the Earth. And the only way that they can reach the surface of the Earth is if they experienced time dilation and they experience time slower than we experience time on the surface of the Earth. So basically, the only way that these muons could have reached the surface of the Earth is if they experience time slower than this guy here. And that actually is what happened. So they're moving so fast, they experienced time slower. They still have that same half-life, but in their perspective, in the muon's perspective, they experience 2.2 microseconds. But for us, because they're moving at the speed of light, and we are just sitting there and we're observing this, we experience their half-life to be longer than it actually should be, but it's not. It's the same for the muon's frame of reference. I'll talk about this more in future videos, but this experiment basically says because the experimenters, they found muons, they detected muons on the surface of the Earth, that means that the muons must have experienced time dilation and special relativity is actually true. Now, there is another experiment as well. So when we're thinking about momentum now, classical momentum is this formula here. The momentum of particles is equal to the mass times the velocity, the product of the two. But when we have particles that are moving, again, near the speed of light, then their momentum won't be so simple. They actually increase their momentum a lot faster. This is what happens in particle accelerators. When particles are accelerated to speeds close to the speed of light, classical physics doesn't predict the momentum using this equation. Classical physics can't use this anymore. We have to start using a different equation, which you'll see in your formula book. We'll go over that more in future videos. It's a lot to wrap your head around initially, but hopefully when we go through some more practice questions, it'll